Energy. No matter what you do, you need energy. Falling asleep to recharge this energy, just like putting our cell phones to charge with a plug. Over time, we spend this energy and we regain it through the fuel in the form of food. Our cities work in the same way we do. They need the energy to operate and use fuel to refill their energy. The less energy, the more sleepy and slow a city becomes. Just like us humans, cities need good quality energy. The better the energy, the better the city will operate, and the better the development will be. The problem in Nevada. Nevada, the driest of all 50 states, and home to the city that truly never sleeps. Las Vegas, home of modern architecture, buildings that scale up to the sky, and the Hoover Dam. A small city that has surprisingly high population density is subject to high demand for energy. Although mostly deserted land, Nevada is home to just over 3 million people. In just one day, these people may require up to 8,000 megawatts of electricity. On the same day, the maximum amount of electricity that can currently be produced is less than 6,000 megawatts. Over the course of 5 years, there were 63 power outages due to human error. In those same 5 years, there were 45 outages due to overdemand. In the year 2017, 86% of the energy consumed in Nevada came from out of state. If this were to continue to happen, Nevada will not be able to develop as quickly as it hopes. The clear issue for Nevada specifically is reliability, consistency, and efficiency in their energy. Other than coal and natural gas, Nevada is powered by solar and hydroelectric as well. Near Primm, there is the Ivanpah Solar Electric Generating System. This uses solar panels to direct sunlight and heat to a receiver at the top of the tower. Southern Nevada has a lot of sunny days, so this, for now, is a viable option. The other big source of energy is hydroelectric, mainly the Hoover Dam. Built on the biggest man-made lake, the Hoover Dam serves its purpose as a dam, but also as an energy source. Although also mostly reliable, there is one issue. The lake's level of water is draining, and there's the fear of not having enough water to produce enough energy soon. This is the reason we need to focus on finding new sources of energy that can help existing ones out. The biggest issue of all is climate change. In the past century, the average global temperatures have risen by 1.3 degrees Fahrenheit. Since the 20th century, this rate of temperature has increased and become faster. In the past 16 years, 14 of them have been the hottest ever recorded in history. Glaciers around the world have thinned by over 10 meters in only 40 years. In 2009 alone, there were 351 reported quote-unquote natural disasters. Turns out that 325 of these are climate-related and are less natural than they seem. All this to say, there's an issue that needs to be addressed with the highest of priority. But there does seem to be a solid step that we can take in the right direction, and this starts with our energy sources. We need to remove energy sources that release greenhouse gases and increase our reliance on carbon-free energy sources. Our current options are hydropower, wind, solar, biomass, geothermal, and finally nuclear. The most promising, with the most room to grow, is nuclear. What is nuclear energy? Nuclear energy is the most powerful yet misunderstood energy source. Nuclear energy was first introduced in 1981 when Enrico Fermi led a group of scientists in initiating the first self-sustaining nuclear chain. Nuclear energy is the energy harnessed in the nucleus of an atom. Nuclear energy is harnessed through either nuclear fission or fusion. Nuclear fission produces energy from the splitting of atoms. This releases heat energy which can be processed into electricity. The most common fuel for nuclear fission is uranium, but plutonium and thorium are also used. Currently, all operating plants in the world use nuclear fission to produce energy. Nuclear fusion is the same process that the sun uses to emit energy. Nuclear fusion is a reaction in which two nuclei collide at high speeds to join and form a new atomic nucleus. During nuclear fusion, not all matter is conserved since some of it is turned into photons, which produces energy. During both nuclear fission and fusion, immense heat is released and is used to turn water from a liquid state to a gaseous state. The steam will then be used to turn a steam turbine generating electricity. In most cases, uranium is used as fuel for nuclear energy as it is the most energy-dense element. Rods are used to control the reaction speed, and coolant is required to make sure the reaction doesn't lead to overheating. But what exactly makes nuclear energy better than its counterparts? For starters, it is carbon-free. No greenhouse gases are released during the process of generating energy. There's also the fact that most of what is used to build the nuclear plant is concrete, which is biodegradable. Other energy sources such as solar and wind use non-biodegradable materials to build solar panels and wind turbines. Nuclear energy also has the advantage of being controllable in its production. Solar and wind energy are inconsistent since they require either sunlight or strong enough wind to move the turbine. Nuclear energy runs over 90% of the hours in a year without any issues and only needs maintenance work once every 18 to 24 months. Currently, all nuclear plants active fall under the light water reactors. There may be a better option that is being worked on though. Molten salt reactors may solve some very big issues for nuclear energy and may be the future of energy. But the answer isn't to completely replace all other energy sources of energy, but to work with them, allowing for solar, wind, hydroelectric, geothermal, and nuclear energy to all work in cooperation to cover for each other and make the most of each energy source. What makes nuclear so good? The best way to figure out why nuclear is as good as it is to compare it to another energy source already in place. The best way to compare it is to use energy sources that are staples in Nevada, primarily coal and natural gas. Coal kills about 100 people per terawatts per hour. Natural gas kills much less with only 4 deaths per terawatt hour. Nuclear power reduces this 4 down to 0.04 deaths per terawatt hour. In terms of efficiency, nuclear beats both coal and natural gas by a large margin. 1 pellet of uranium, the size of the tip of your finger, has the same amount of energy as 17,000 cubic feet of natural gas, 1,780 pounds of coal, or 149 gallons of oil. A study done by NASA showed that nuclear power has actually saved over 1.8 million lives, although not directly. Using nuclear power over fossil fuels means less air pollution, which led to over 1.8 million lives that were spared. NASA projects that another 7 million lives may be saved over the course of the next 4 decades. In the entire history of nuclear energy production, there have only been 3 major disasters: 3 Mile Island, Fukushima, and Chernobyl. In the past 25 years, there have been over 7 major disasters with fossil fuel energy, the largest of which was the BP oil spill, which still affects wildlife today. What are the negatives of nuclear energy? Nuclear energy has 3 main problems: fear, expense, and waste. While exploring the notion of fear that revolves around nuclear energy, I had the privilege of talking to Joe Lasseter. Joe Lasseter is the Senator John Haynes Professor of Management Practice and Environmental Management and is now retired. He focuses on finding carbon-free energy sources that are affordable. While talking to him, he enlightened me that the fear that revolves around nuclear energy is more generational than anything. People who lived through World War II and dealt with the fallout seem to hold fear of a nuclear war. Newer generations are less fearful of nuclear war, but focus a lot on past disasters such as Chernobyl and Fukushima. While researching, I realized that fear is just a lack of information. The more people learn about nuclear energy, the less they fear it. While talking to Joe, he expressed how much the cost of nuclear energy is holding back its advancement into the commercial scene. Each power plant can cost anywhere between $6 to $9 billion to construct. Once built and operating, costs for electricity become cheaper than coal, but the initial investment is holding back nuclear energy. I also had the privilege of talking with Matthew Wald, the communications advisor at the Nuclear Energy Institute and former New York Times reporter. While talking to him, he explained to me that recently, due to fracking, electricity has become cheaper. This is making businesses want to continue with fossil fuels since they have no financial reason to move away from it. An option is small modular reactors. These are reactors built in factories that produce less energy than normal reactors, but are much cheaper. Other than small modular reactors, there may be a solution that not only reduces cost, but may also help find a solution to the last problem: nuclear waste. Another subject that Joe and I touched on. He said that nuclear waste is misunderstood by the community. During the process that is undergone in light water reactors, only about 7% of the uranium is burned. The other 93% is absorbed by the rod, which is then disposed of. This nuclear waste is surprisingly easy to handle compared to other wastes that we manage. In the history of nuclear energy, nuclear waste has never killed anyone. Every other industrial waste we manage and dispose of has killed someone. Breaking down Chernobyl. Chernobyl is the worst nuclear disaster and is the reason so many people fear nuclear power. But what exactly happened at Chernobyl, and can it happen again? The main thing to take away from Chernobyl is that there are no corners that can be cut. You cannot risk safety just to make something cheaper. Before I can explain what happened, here are terms that you need to know. Protons. Protons are particles that determine the element. Neutrons are particles that stabilize the element. While the number of protons determines the element, the number of neutrons can change and the stability will change with it. Isotopes are the words used to describe the same element with different amounts of neutrons. Unstable isotopes is what occurs when there are too many neutrons or too few neutrons. It will emit energy and particles on its road to becoming more stable. This process is called radioactive decay. Radioactive decay is one of three nuclear reactions alongside fusion and fission. Radioactive decay is the process of an unstable isotope becoming stable by releasing energy and particles. Heat is produced by radioactive decay. Even after a reaction, the radioactive decay will continue to produce heat. The heat will go into the fuel, but if you do not have a coolant to cool off the fuel, it will melt itself. They will continue to heat themselves up until they become stable. This can melt through just about anything and is called a meltdown. Uranium-235 is a special isotope that has a very neat ability. If uranium-235 is hit with a neutron, it will split apart and create more neutrons. If those neutrons hit another uranium-235, the cycle continues and it will cause a nuclear chain reaction. This chain reaction is why we have nuclear power. This is also how nuclear bombs work, but that's not what we want when using uranium for energy. We need to control the speed of the reactions using control rods and coolant. The issue is that uranium-235 is rare, and we need to enrich uranium to be able to produce a good amount of energy. This process turns out to be quite expensive, and the RBMK was a reactor used at Chernobyl, and the idea of it was to be cheap. That's the first issue with Chernobyl. The RBMK did everything in its power to make itself cheaper, and that in turn became its downfall. Now that we know this, we can go back to what happened in Chernobyl. In Chernobyl, when the workers went to test the backup cooling system, the routine went wrong. To work on the reactor, workers lowered the reactor's capacity to 25%. The issue occurred when the reactor dropped to 1%. This occurred since xenon-135 is on the pathway of radioactive decay for uranium. Xenon-135 absorbs the neutrons and this halted the power supply. More xenon-135 is present the longer the reactor is operating. Unfortunately, the workers had the reactor working all day before the test, so the amount of xenon-135 was much higher than normal. Since the reactor was no longer producing energy, the workers chose to bump it back up to normal capacity. To speed up this process, they removed the control rods that controlled the speed of the reaction. When they bumped it back up, control rods made of graphite weren't in place, making the reaction too fast and caused a power surge. The workers were unable to control the reaction and weren't able to control the coolant that kept the reaction safe. As temperatures rose higher and higher, the core was melted and the reactor exploded. This can also be credited due to the high pressures that occurred due to built-up steam. Air started to leak in, which caused the graphite fire. One of the workers insisted on aborting the test, but one of his superiors told him to carry on, which made the end result worse. Initially, there were 31 deaths due to acute radiation sickness. The big issue is that civilians weren't told about the radiation until more than a day after the explosion. Thousands of people lived a full day normally with a lot of concentrated radiation in the air. There are about 4,000 more deaths that are blamed on radiation exposure from Chernobyl. Currently in the area of Chernobyl, the problems are economic and psychological, and no longer are issues of health due to radiation, says radiation expert Balanov. He says that the number of people affected was overestimated by about 800,000 people. Since both Chernobyl and Fukushima, multiple new guidelines and restrictions have been added to the regulation. The IAEA, International Atomic Energy Agency, has come out and said that another accident like these two will not happen again. Nuclear reactors are no longer built to be as cheap as possible and focus on safety over affordability. Although what happened in Fukushima was different than in Chernobyl, the IAEA has also made new regulations to make sure that another Fukushima doesn't happen. Molten salt reactors. A solution that may be able to fix most issues with nuclear energy, molten salt reactors. While talking to Joe last year, he explained to me all the benefits of molten salt reactors compared to light water reactors. In the normal or basic molten salt reactor concept, the fuel is a molten mixture of lithium and beryllium fluoride salts with dissolved low-enriched uranium-235 or 233 fluorides. Heat is transferred to a secondary salt circuit and thence to steam or processed heat. The most notable thing is that molten salt reactors operate at atmospheric pressure compared to light water reactors that require very high pressures. High pressure may cause explosions if there is a failure. Molten salt reactors do not have this issue. To achieve the high pressures that light water reactors need, many special and expensive materials are needed. Since molten salt reactors run at normal pressure, they are cheaper since they don't need these extra materials and become cheaper to build. Although nuclear reactors are already much more efficient than other energy sources, molten salt reactors operate at much higher temperatures than light water reactors, which boosts efficiency. Molten salt reactors are also safer than light water reactors. The fuel and coolant salts are chemically inert, and no firing or explosive with air or water. The boiling point of fuel salt is about 1,670 kelvins or more, much higher than the operating temperature of 973 kelvins. Therefore, the pressure of the primary system cannot increase, meaning what happened at Chernobyl cannot happen. Molten salt reactors are safer thanks to physics instead of highly complicated and advanced engineering. Molten salt reactors burn more of the uranium used than light water reactors. This means more of the uranium is used and less is thrown away as nuclear waste. On average, only 70% of uranium is used, while 93% gets thrown away as nuclear waste. Molten salt reactors can increase efficiency. They can also reuse some of the spent fuel from current light salt reactors. Molten salt reactors may be the solution to multiple problems, and companies like Thorcon are already starting to develop the idea further. Nuclear diamond batteries. The issue of nuclear waste may also have a solution, but it would be on a much smaller scale. The answer may be in nuclear diamond batteries. Nuclear diamond batteries are batteries that use nuclear waste along with diamonds to create energy. They do this by abusing the constant and long-lasting beta decay that occurs in nuclear waste. When this beta decay is close to a diamond, it is turned into an electrical current. Beta decay can last up to centuries and millennia, so these batteries would last longer than anything we are used to. The main issue is that the amount of energy produced is less than optimal. These batteries can be used on different scales from your smartphone to your car, and can even power spaceships if enough was used. This continuous energy will power smartphones for hundreds of years and can currently power a car for an estimated 90 years. While talking to Matthew Wald, he said that at the moment, with the current technology, diamond batteries can power mobile devices, but won't make enough of an impact on the disposal of nuclear waste to be considered a solution. Even if not a viable option for disposal, it is a neat invention that may be useful in some aspects that can be built off of nuclear waste. The biggest issue is that diamonds are highly valuable and are used for jewelry instead of technology. If we could find something as effective but cheaper, it may become more viable. How does nuclear energy benefit Nevada? Nevada is a dry state with a hot climate in the south and a cold climate in the north. Since the change in temperatures and climate are so drastic, most energy sources cannot be used in both areas. Solar thermal towers lose most of their energy in cold climates, while natural gas has a risk of freezing in colder climates. Recently, there was an example of this. In Texas, the power grid failed due to cold temperatures. This caused the state many issues economically, and people became irritated with the lack of a reliable power source. Unlike both natural gas and solar thermal power towers, nuclear energy doesn't rely on outside factors, nor does it fail in extreme conditions. Nevada is a state with low natural disaster rates, but it is a state that is often in drought. Now that wind droughts are on the uprise, wind power is no longer a reliable option. Nuclear will not only provide stability, but independence from other states. With the amount of open desert in Nevada, there is no issue with building nuclear plants other than cost. If the issue of cost is figured out, then nuclear power will be the most obvious choice of energy. Between efficiency, reliability, sustainability, and overall energy production, nuclear power solves all of Nevada's issues. Nuclear Nevada. Nuclear energy is still new and developing. As we progress into a new era of energy, we need to forget energy sources that emit carbon and look to carbon-free sources. Although I believe nuclear energy is a big part of the answer, nuclear alone will cause problems. Variety and diversity will always be better options. Using carbon-free sources such as solar, wind, hydroelectric, geothermal, and nuclear is key in slowing down climate change and pushing forward progress. New innovations and inventions such as molten salt reactors and diamond batteries are what will allow us to keep moving forward and make the right changes we need to better our energy options. Nevada is still young with plenty of land to grow outward on. Hopefully with new energy sources, development will be expedited and will become more efficient. The other thing we need is knowledge and information. Fear is just the lack of knowledge, and people won't support something they fear. Teaching people about energy and the options within energy will make it easier to push forward socially. The last component we need is investors. People willing to take a chance to make a change. These people need to also be informed and need to know what they are investing in will bring success. Nuclear energy is a new technology with a lot of potentials, but fear revolves around it. With the public being more informed, investors will be more willing to invest since the fear that lurks around nuclear energy will be gone. The goal is not to convince people that one source of energy is better than another. The goal is to spread knowledge and information for people to decide on their own. The goal is to better the future, to live longer, and to protect the home we call Earth.